Okay, so we will talk about pressure. And so the reason we're talking about pressure is when we want to make fluids flow. So let's say here's a blood vessel, and you want blood to flow. What you need is a higher pressure here and a lower pressure here. Okay, so you need to have a pressure difference. A fluid will flow from high pressure to low pressure. Okay, and greater the pressure difference, higher the flow rate. Okay. And we'll learn that wider the pipe, greater the flow rate. Flow rate is how many gallons a minute are flowing and so on, or how many liters a minute are flowing. So that's what this thing is. That's what this chapter is about. Okay. And like I said, I'm going to quickly go over some of the slides. You guys have seen, you probably have had a chance to go over the recording from last week, but this will sort of be a review. So pressure is defined as force per unit area. Okay? And the units would be, force are measured in newtons, area in meter square. Those are the SI units. Okay? Newton per meter square. And this is called a Pascal. Okay? So the units for pressure, SI units for pressure are pascals. You want to remember some of these units. Okay, 1 atmosphere is 10 to the power 5 Newton meter square, that is pascals. 1 atmosphere is 100,000 pascals. You probably also have seen this. 1 atmosphere is 15 pounds per square inch. Okay, so do you guys know the pressure in your tires? Yeah, 35 psi, so about 2 atmospheres. Okay, so and we'll come to this in a little bit, but the 35 psi in your tire is a gauge pressure, which is so gauge pressure. It's called a gauge pressure because gauges measure that pressure. It's the actual pressure minus the atmospheric pressure. So when you say it's 30 psi in your tires, that's 2 atmosphere, but that is this guy. So it's really 3 atmospheres minus 1 atmosphere. Okay, so the actual pressure in your tire is 3 atmospheres. Okay. All right, anyway, so here's 1 atmosphere, which is 15 pounds per square inch. Okay, what does that mean? So here's a square inch. Okay. And so let me show you, where are we? Okay. So you saw in the recordings, how does pressure arise? One way to look at pressure is, so in this room there are air molecules and they're bouncing off the walls. And when they're bouncing off the walls, the wall exerts a force on the atoms, and the atom exerts an equal and opposite force on the walls. Okay, so there are billions and billions of molecules bouncing off the walls, and they exert a force of 15 pounds per square inch. Okay? So the air molecules bouncing off this square inch are exerting a force of 15 pounds per square inch. Okay? And so now here's the amazing part. Okay, so if you look at this sheet of paper, okay, this is absolutely amazing. How much is this? How big is the sheet? 10 inches by 10 inches. That's 100 square inch. So 15 pounds times 100. Okay. So the total force on this thing is 15 pounds per inch square times 100 square inch. Okay. So that is 1,500 pounds. That is the force on this paper. The force of the air molecules bouncing off on this paper is 1,500 pounds. That's the weight of 10 people. Why isn't this flying away? What's that? I can hold it with a force equal to the weight of 10 people? No. Why isn't this flying away? Or, very good. There's 1,500 pounds here, and there's 1,500 pounds here. Okay, so that's why it's not flying away. Okay, so similarly, on your chest, you know, the atmosphere is pressing down on you. Why aren't you collapsing? Inside your lung, there's air at 1 atmosphere that's pushing up. Okay? All right, so what you'll learn in a second, if you saw the recording, if you go underwater, if you go 33 feet underwater, now the pressure on you is 2 atmospheres. Now it's 30 pounds per square inch. On an area like that, what would be the force? 3,000 pounds. You better have 3,000 pounds on the other side. So does anybody dive? Yeah. So if you go diving, if you're 33 feet underwater, what do you have to do? You have to breathe air at 2 atmospheres. If you're 66 feet underwater, you have to breathe air at 3 atmospheres. Very good. Okay. And you guys probably know this, that you've at least heard of this. When you breathe air under higher pressure, more air is dissolved in your blood. Okay? And if you come up too fast, that dissolved air will come up, bubble up. And if those bubbles collect in your joints, that hurts. Okay? So you have to come back slowly. Okay. Okay, there's pressure. So what you want to remember is some of these numbers. 1 atmosphere is 10 to the power 5 pascals. 1 atmosphere is 15 pounds per inch square. 1 atmosphere in millimeters of mercury is 760 millimeters of mercury. We'll talk about what that is. It's also 76 centimeters of mercury. This is a unit that's often used in the medical industry. So the blood pressure, when they say it's 120 by 80, what do they mean? What are the units? It's 120 millimeters of mercury by 80 millimeters of mercury. Okay? And that is a gauge pressure. We'll see this. Okay. Now, here's the deal. Now, so let's say here, if you push this person with a force of 15 pounds, and you push the same person with a force of 15 pounds using a needle, which one hurts more? It's obvious, the needle hurts more, but it's the same force. So what's going on? What's that? So here's what's going on. The pressure is force divided by area. Okay. The area over which that force was applied was much smaller. The pressure was greater, and greater pressure breaks the skin. Okay. And so that's what was happening. So it's too high a pressure will break your skin. Okay. Now, fluids and solids can exert pressure. Fluids, what is a fluid? Air is a fluid, blood is a fluid, water is a fluid, and all that. Okay, so if here's the thing about pressure. No matter what the shape of the sheet of paper, the pressure is always perpendicular to the surface. Okay, so the pressure is always perpendicular to the surface, so the force will always be perpendicular to the surface. Okay. Now here's another way of thinking. So there are 2 ways of thinking about pressure. It's air molecules bouncing out the wall exerting the force. Okay. You can also think of pressure as the following. So the pressure here is 1 atmosphere, and that is the weight of this column of air all the way to space. Okay, that's pressure. Okay. So if you were at the top of this column of air, what would be the pressure there? So let's say space is up to 100 kilometers. The pressure here is the weight of this column of air. Okay, let's go to a height of 100 kilometers. What is the pressure there? There's no more air on top of you. The pressure there would be 0. Okay? Did you guys understand that? Okay. Now it turns out that the air column is heavier at the bottom and it gets lighter and lighter at the top. There's less and less air. So actually, if you go about 5 miles up, the pressure is half an atmosphere there. Okay. So the first 5 miles has half the weight, and then the other half is the rest of the way up. All right, again, we've already answered this question. What this problem shows you is the following. Okay, so there's a large pressure. Okay, atmospheric pressure is pretty large, and it's exerting a force like that. Pressure is force divided by area. So force is pressure times area. Okay, so the force that the atmosphere exerts on this wall, that's what's shown here. It's 10 to the power 6 newtons. That's 1,000,000 newtons. That's roughly the weight of 10 school buses. Okay, this is a wall of 10 meter square area. 10 meter square is roughly half this wall. So the atmospheric pressure on half this wall is the weight of 10 school buses. Okay, that's what this problem tells you. Okay, again, why is this not collapsing? Because there's an equal and opposite force on the other side. Okay. All right. Again, like I said, I'm quickly going over some of these slides. So, this is sort of a review. Okay. So, what this formula tells you is, if you have a gas in a chamber. Okay. Let me pull up that. Okay, so we have a gas in this container. The temperature is 300 degree Kelvin, which is roughly the temperature in this room. The pressure is 35 atmosphere. That's a huge pressure. Okay. This container has to be pretty strong to hold a gas at that temperature. Okay, and you see, you could potentially count the number of air molecules here. Okay, so N is the number of moles of gas there is. Okay, what this formula is telling you is the pressure, volume, and temperature of the gas are related by that formula. Okay, no matter what you do, okay, they'll always be related and little n is the number of moles of gas, R is the gas constant. Okay, so in this is called the ideal gas law, and one of the things you want to notice is, if you keep the temperature constant and the amount of gas is constant, this would be constant. So if this guy is constant, you raise the pressure, the volume would have to decrease such that the product remains constant. Okay? All right, pressure, volume, number of moles of gas, and this. All right. Now I'll show you something. Let's say we'll keep the volume of the gas constant. If I double the temperature, what will happen to the pressure? If I increase the temperature, what will happen to the pressure? So I'm keeping the volume constant. This is constant. Very good. Okay, so I'm going to double. If I double the temperature, the pressure should double. Okay, so let's see that. Okay, so watch this number. There's the temperature, 300 degree Kelvin, and I'm going to raise the temperature to 600 degree Kelvin. What is the pressure? 35 atmospheres. So it should go to 70 atmospheres. Okay, so let's see that. So I'm warming the gas, and you see the gas molecules are moving faster and faster, and the pressure is increasing because they're hitting the walls at a faster speed. Okay? And it all makes sense. Yeah. Okay, there we go. So I've doubled the temperature and the pressure doubled. Okay? Yep.
When they crash together, the molecules, does that will like slow them down eventually to where the gas dissipates?
No. They have the same kinetic energy. They're all elastic collisions. So there's billions of collisions going on. You played pool. So you hit the cue ball with the stationary ball. Whatever speed the cue ball is going, if it's a head-on collision, the ball you hit goes at the same speed. Okay? So, all right, so this is the ideal gas law. All right, so we saw that pressure can be thought of as, pressure can be thought of as the weight of this air column all the way to space. Okay, so now let's go underwater. Okay, so let's say we go underwater. What is the pressure here? The pressure here is the pressure of this column of air all the way to space, and that's P naught. And then the weight of this column of water. Okay, so the pressure at this point is the pressure of this column of air plus the weight of this column of air of cross-sectional area 1 meter squared. Okay, that's P naught is the pressure due to the atmosphere, and this is due to the fluid. Okay. Now, if this were water, if you go 33 feet deep, this will equal that. That's 1 atmosphere. Okay, so that's what we mean. If you go 66 feet underwater, this will equal 2 atmospheres. Okay. If this were mercury, you go 76 centimeters under mercury. Okay, so if it were water, see the density of water. The density of water is 1,000 kg. 1,000 k. 1,000 kg per meter cube. The density of mercury is 13,600 kg per mercury. Mercury has a much higher density. So you only have to go, for water, you have to go 10 meters. 10 meters. For mercury, you only have to go 0.76 meters, okay, or 76 centimeters, or 760 millimeters. Okay. So, because the density of mercury is much higher, 13.6 times higher, you go 13.6 times less. Okay. So this is giving you the pressure inside a fluid. So there is the atmospheric pressure, and there is the pressure due to this column. Okay. So that's the pressure at a depth in a fluid. Okay. Okay, most gauges, what they do is, most gauges do not measure the actual pressure. So the actual pressure is this. What they do is they measure the actual pressure minus atmospheric pressure. Okay? And that's called the gauge pressure. Okay. So the gauge pressure is absolute pressure or actual pressure minus atmospheric pressure. So gauge pressure is absolute pressure minus atmospheric pressure. Okay. So actual or absolute pressure minus atmospheric pressure. Yep. So when you in your doctor's office, they tell you the pressure is 120 millimeters of mercury. That's a gauge pressure. Okay. So the actual pressure of your blood is so the high blood pressure is 120 millimeters of mercury, and the atmospheric pressure is 760 millimeters of mercury. Okay, so your actual pressure is 880 millimeters of mercury. Okay. All right. Now, since in the medical industry we are always talking about gauge pressure, we shall use the convention that all pressures are gauge pressures unless otherwise specified. So the blood pressure that they measure in the doctor's office, the ocular pressure that they measure, all are gauge pressures. Okay. So here is an IV system. What is the idea of this IV system? What are you trying to do? I'm sorry? You're trying to get this fluid into your bloodstream. Okay? All right, so here's the needle. I've drawn a needle here. Again, the tip of the needle is inside your blood vessel. Okay. And this is the outside of the needle. Okay, here's the blood is, what is the high pressure on your blood? 120 millimeters of mercury. Okay. Now, if you're trying to push this fluid inside your bloodstream, so here's 120 millimeters of mercury, what do you need? You need a higher pressure here to push this fluid in, okay? So I'm just going to make up numbers. So if you have 130 millimeters of mercury, then this fluid will go into the bloodstream, okay? And if this bottle is too low, that pressure won't be high enough, and this fluid will not go in. In fact, if this pressure is lower than that pressure, blood will flow out, and you can see that blood coming into the IV, into the tube. Okay, so if this fluid is not flowing in, all you do is raise this up to increase this pressure. Okay, so that's what's going on. All right, I'll skip this portion. All right, here is an important law, a Pascal's law. So here's an enclosed fluid, okay? And you saw that, so there's atmospheric pressure there. So for now, let's say the piston is not there. The piston is not there. So, and then as you go deeper in the fluid, the pressure increases, and then back to atmospheric pressure, okay? What Mr. Pascal realized was for a fluid that is enclosed, if you increase the pressure, let's say you can increase the pressure by applying a force like that. So you apply a force, and P1 is force divided by area 1. So let's say you push on this piston, and A1 is the area of the piston. You increase the pressure at this point by P1. And I'm going to put a number on that. So let's say you increase the pressure by 0.2 atmospheres. So what Mr. Pascal realized was, if you increase the pressure at any point by 0.2 atmosphere, at every point in the fluid, the pressure increases by 0.2 atmosphere. Do you guys understand that? So that's what that's Pascal's principle. You have an enclosed fluid. At any point, you increase the pressure by a certain amount. At every point, the pressure increases by the same amount. So the pressure here also increased by the same amount. Okay? So and the pressure is, so you're pushing this piston with a force of F2 divided by A2. So that has to equal that. Well, what is the point of this? So now I'm going to solve this. I'm going to solve for F2. F2 will be, I'll bring A2 over there. Yeah. Okay. F2 is A2 over A1. Okay, now you don't have to remember any of these formulas, but you want to understand the concept. Okay, this is a circular piston area. Okay, so F2 is pi, R2 is the radius of that guy square divided by pi R1 square, F1. Okay, don't get lost in the math. I want you to remember the punchline. Okay, all right, so F2 is R2 over R1 square times F1. Okay, so let's say this input piston is 1 inches wide, and this output piston is 5 inches wide. 5 divided by 1 is 5. 5 square is 25. The output force is 25 times the input force. So this is a force multiplier. You apply a force of 100 pounds, you're getting an output force of 2,500 pounds. Did you guys understand that? That's how they lift a car when they get an oil change at the mechanic.
That's how hydraulics work.
Yeah, that's how hydraulics work. They don't have Superman in the back. This is how, when you're sitting on a dentist chair, the dentist is pumping a pedal. He's pushing on this and lifting the patient in the chair. Okay? So whenever you want to apply a large force, okay? Yeah. So this is a force multiplier. Okay? So now the question for you is the following. It sounds like free lunch. It's not free lunch. What is the price you're paying? You got to pay the piper. What gives? Okay, so it turns out here's the deal. The work done is force times distance. You apply a smaller force, you have to apply a greater distance. So for the patient to move just a little bit, the dentist has to pump several times. You have to move several times. Okay. So the small force has to move a large distance where the output force will move a small distance. Okay. So if the force gets multiplied by a factor of 25, the distance gets multiplied by the inverse of 25. Okay. So if the output force is 25 times greater, the input distance has to be 25 times greater. So to move the patient 1 inch, you have to pump 25 inches. Okay, so that's what's going on. But this is an important thing that we use in medical industries and in our everyday life. This problem illustrates that. This is a problem on the dentist chair. See, this is the, and again, so the cylinders are, so where are the numbers on the cylinders again? Okay, so 5 centimeter diameter and 1 centimeter diameter. So this guy has a diameter 5 times greater than that. It has an area of 25 times greater than that. So this multiplies by a force by 25 times. Okay, so you're lifting at 1200. This is 1200 Newton person and the chair, and applying only a 50 Newton force. Okay, so you're getting a force multiplication of 25. Okay, so when you measure blood pressure, so when you walk into a doctor's office, the first thing they do is measure your blood pressure. Okay, so measurement of pressure is an important indicator of health. Okay? So that's one of the first things you measure. And so here's the thing. So here's the correct way of measuring the pressure. You put the cuff at heart level. Okay, and what you do is, and the stethoscopes need to be placed there. So now let's. So this is the blood pressure. Okay, so let's say your blood pressure is 100, maximum pressure is 120 millimeters of mercury. Okay, so if I apply a pressure of 130 millimeters of mercury, what will happen?
It'll contract your arm,
I'm sorry?
will squeeze the muscle.
The blood vessel will collapse. All flow, blood flow will stop. So that's what they're doing. When you apply the pressure, what you do is you collapse the blood vessel, and you're listening to that, and flow has stopped. Okay? And then you slowly release the pressure. When this pressure gets to 120 millimeters of mercury, this starts expanding and blood flow starts. And that's what you're listening to. Okay, so when the first flow starts, that gives you the high pressure. That gives you the systolic pressure. Okay? And you guys following this? Okay. And when the pressure, the minimum pressure is 80 millimeters of mercury, when this pressure decreases to 79 millimeters of mercury, the blood vessel is completely expanded and flow is completely normal. Okay? And so you hear that as a change in sound as well. Okay? So that's how blood pressure is measured. Okay, has anybody had a spinal tap? Okay. I'm sorry?
For a C-section, it seems like you did something different with epidural for me. I want to say it was something.
They put a needle on your spine? Did it hurt like?
My first child, my epidural did not work.
Okay.
So I didn't really
Yeah. When I was a kid, I had some kind of meningitis, spinal meningitis, and that hurts like crazy. All right, so here's the point. Okay, so on the cuff, when you're measuring the pressure, okay, this is transmitted by air. Air doesn't weigh much, so this gauge can be anywhere you want. Okay, the air hardly weighs anything. So this gauge can be anywhere. But when you're measuring the pressure of your spinal fluid, this is transmitted by saline. The pressure is transmitted. And that gauge has to be at exactly the level where you're measuring the pressure. Okay? Do you remember that? Well, I guess you can't see that.
No, because I had to get like 3 because I couldn't get it. And I had to do anesthesia the 3rd time because I just like couldn't do it. But one was in the emergency room and then one was when I was like in the ICU.
So you cry for pain, huh?
Oh, it was bad. Oh, it was bad.
Yeah. Oh, I can't believe it. Yeah.
Yeah.
Yeah. So for the spinal tap, it's a saline solution that's transmitting the pressure, and the gauge has to be at the same level. Okay, just a manometer measures this pressure, the gauge pressure. It measures the absolute pressure. It's minus the atmospheric pressure. Okay. So this is what's used to measure blood pressures. Yeah, that's what a manometer does. A barometer measures the actual pressure. Okay? So that's the difference. Okay. So this is what's used to, a barometer is what's used to measure the atmospheric pressure. The weatherman uses this. And a doctor uses a manometer. Here's how a barometer is built. Okay, you take mercury, so what you do is you take a tube like this. It has to be 1 meter long, 3 feet long. Okay? You fill it with mercury, and then you don't put your thumb on it, but I'm just saying. You put your thumb on it, and then invert the tube there. Okay? Okay, so this is the column of mercury. This is 760 millimeters. Okay, that's 76 centimeter. And this is the most perfect vacuum you can have. This will be vacuum. So there's no air there. It's only this column of mercury. And that 76 centimeter of mercury is balancing a column of air of equal width. This air all the way to space is being balanced by this mercury. And that's 1 atmosphere. Okay? Do you guys understand that? Okay. So, so 1 atmospheric pressure is 760 millimeters of mercury. Okay? So when your blood pressure is 120 millimeters of mercury, that's about 15% of the atmosphere. Okay? I'll have to rush a little. Okay? I'm sorry. You guys know what an aneurysm is? Okay, so here's a blood vessel. This wall weakened, and then this will bulge. So a weakened wall has bulged. Okay. Now let's look at this. Pressure is force times area. Force is pressure times area. Okay, see, when the wall bulges, the area has increased, right? I mean, you can see that the area is in. The pressure is the same. The wall is already weakened, and now because the area increased, the force has increased, the total force has increased. A bad problem is getting worse. Okay? And here's another thing that happens. You'll learn this toward the end of the chapter. Flow gets turbulent. When flow gets turbulent, the flow rate decreases. To compensate for that, your body increases the pressure. You get an aneurysm, that you're on a slippery slope downhill. Okay? The area increased, your body, because the flow rate decreased, the body increases pressure. There's a larger and larger force on it. And this, if this busts, that's bad news. Okay. So this problem goes through the calculation, okay? And that is the force, 46 Newton, 15 newtons is the force on an aneurysm that is, what is the size of the aneurysm? So there is the blood pressure of the person, 140 millimeters of mercury, high blood pressure. So this, do your best to keep your blood pressure within acceptable limits if they suspect you have an aneurysm. Okay. All right. So where is the? Okay. So 25 centimeters squared. So the aneurysm is about that big, and the force on the walls of the aneurysm is 15 newtons. 15 newtons is 22 pounds. On a thing like that, 22 pounds. Good luck, right? All right, so you saw that if you go underwater, the pressure increases. Okay, the pressure down here is higher than the pressure there. So if you immerse any object in a fluid, it will feel an upward force. And that's called a buoyant force, okay? So if you immerse this object, well, there's the weight of gravity and there's the fluid pushing you up. So if the weight is greater than the buoyant force, then the object will sink. A stone will sink. If this was a piece of wood, the buoyant force is greater than the weight, and so that will rise. If the buoyant force is equal to the weight, then this can remain suspended underwater. Okay, and for us, for human bodies, the buoyant force is almost exactly equal to our weight. So if you were underwater, you would be weightless, and if you didn't panic, you wouldn't sink. Okay? But anyway, so Mr. Archimedes says how large this buoyant force is. and the buoyant force is equal to the weight of the displaced fluid. Okay, so you displace this much fluid, this buoyant force is equal to the weight of this much fluid. Okay? For any object to float, the density of the object has to be less than the density of the fluid. Okay, that's when an object will float. So the object's density has to be less than the density of the fluid for it to float. Okay, and what this formula tells you is, so if the object density is less than the density of the fluid, this tells you how much object is underwater, and that's the total volume of the object. Okay, so for an iceberg, the density of ice is 90% the density of water, and so 90% of the iceberg is underwater. Okay, that's what that tells you. Okay. So here's a pipe. Okay. I want to make fluid flow in this pipe. So you learned that you have to have a high pressure here and a low pressure here to make the fluid flow. Okay. Now, let's say I'm going to take two identical fluids. I'm going to maintain the same pressure. And I want to measure flow rate. Flow rate is how many gallons are flowing a minute. Okay. I'm going to pump water and honey. The pressure difference is the same, pipe width is the same, and so on. Which will have a greater flow rate? I'm sorry? Oh, yeah, water, right? All right, so the flow rate is denoted by Q. It's the pressure difference divided by the resistance. Greater the resistance to flow, lower the flow rate. Okay? So obviously, honey has a greater resistance than water. Okay? So here is the resistance. Here's the formula for the resistance. And again, you don't have to remember any of this. This is the number that's different for different materials. This is eta. And for honey, eta for honey is higher than eta for water. Okay? So the resistance depends on this thing called viscosity. That's viscosity, the length of the pipe, and the radius of the pipe. Okay, so here is the most important part for medicine. So let's make sure we understand this. Okay. You want to increase the flow rate. What you can do is you can increase to increase the flow rate, you can either increase that or decrease that. All right? Okay, to increase that, you want to maintain a larger pressure difference. Your heart has to work harder. Okay? So you want to put a higher pressure here. And remember, if you had an aneurysm or something like that, you don't want to raise your pressure, right? So you could increase your pressure, or what else can you do to increase flow rate? Decrease R. Okay? So when would you want to increase blood flow rate? You have a meal, you want to increase the flow rate to your digestive system. You go for a run, you have to increase flow rate to your muscles. Okay? And so on. You're running away from a tiger, you want to increase flow rate to your muscles. Okay? All right, so here's how we increase flow rate. You want to decrease R. If you increase the radius of the blood vessel, you increase the radius of the blood vessel, you can increase the flow rate. Okay? And that's what we do in our body. Okay? So this problem, here's a very important problem. I want you to just remember the results. So when a person eats a large meal, increased flow rate, the digestive system is, blood flow to the digestive system is increased by dilating blood vessels. So here's flow rate is increased from 1 liter a minute to 5 liters a minute. you've increased flow rates by a factor of 5. Okay? So you have increased Q by a factor of 5, and that's by decreasing R by a factor of 5. Okay? So you increase flow rate by decreasing resistance. Okay, and it turns out so you increase flow rate by 5 by increasing the radius, dilating the radius only 50%. Okay, so in your body, you control flow rate by either increasing the diameter, or if you want to constrict blood flow, what you can do is if you want to decrease flow rate, you can constrict the blood vessels. When do you want to decrease flow rate? You'll want to do that soon. Huh? When you're cold, you don't want blood to flow to your extremities, and that's when you constrict the blood vessels. Okay, so by just dilating and constricting blood vessels, you can control flow rate. Okay, and that's the most important. So this is very important. Okay, so again, flow rate is the pressure difference divided by the resistance to flow. Okay, and that formula has been put here. The whole thing is put here. So, and by the way, this thing didn't come through properly. Q is P2 minus P1 divided by 8 eta L, and that's pi r to the power 4. Okay, I've got to fix that. All right, so you increase flow rate by increasing the radius of the pipe. You decrease flow rate by decreasing the radius of the pipe. Okay. And again, a 50% increase in the radius increases flow rate by 500%. Okay. Okay, real. You scare her away? Man. All right. So this is called laminar flow, and this is called turbulent flow. When the flow gets turbulent, the resistance increases. Okay, so if in your blood vessels you have turbulent flow, the resistance is increased and the flow rate has decreased. Okay? So if you want to maintain a flow rate, then you have to increase the pressure. Your heart has to work harder. Okay? So when you have an aneurysm, the flow will become turbulent there. Flow rate decreases and you increase pressure. But that's bad for you. Okay? So turbulent flow is not very good. Okay? You have to work harder and so on. So what you want to do is maintain laminar flow. Okay? So heart murmurs are sounds produced by turbulent flow through a defective heart valve, okay? Or a hole between heart chambers. Okay? Okay, so it's often possible to hear turbulent flow because the sounds made by the eddies. When you hear, so turbulent flow has many eddies, okay? So when you hear water running somewhere in your home, the sound is turbulence, usually in the valves, okay? And so anytime you hear fluid flowing, that's because of turbulence, okay? Modern cars are designed to cause minimal turbulence to avoid extra resistance. Whenever there is extra resistance, what does that mean? You're using more gas. Okay? You're getting less mileage, gas mileage. Okay? Aircraft, ships, and submarines are similarly designed, and the shape of fastest birds and sea life are such as to create very little turbulence. Okay? Turbulence, so turbulent flow causes higher resistance, okay? And you have to work harder for the same flow rate. Turbulence is also caused by large fluid speeds. Okay, so if something flows If a fluid flows too fast, then it'll become turbulent. Okay? Above a certain critical speed, friction between the fluid and the walls of the tube start eddies. Okay. Commercial aircrafts are flown at less than top speed for this reason, because they're trying to avoid turbulence. Okay. Okay. I'll let you guys read that. That's not important. So if a fluid is flowing fast, then turbulence will set in. So you want to know when turbulence will set in. Okay, so to be below that speed. Yeah. And there's a number called Reynolds number that tells you when turbulence will set in. Okay, here, so you can see this. This is the Reynolds number. And here is an object that's going through a fluid. This is turbulent flow. So the object is moving this way, and this is turbulent flow. Whenever this turbulence happens, there's more drag to it. You have to put in more effort to go forward. So for instance, if you're driving less than 55 miles an hour in your car, there's very little turbulence. Above 55 miles an hour, there's a larger turbulence, and it costs you more and more. The faster you go, it costs you more and more. Okay. All right, so the Reynolds number depends on the density of the fluid. This is the size of the object, the diameter of the object. V is the speed of the object, or you can have a still object and the fluid move in the other direction. It's the same thing. And this is the viscosity of the fluid. Okay. Eta is the viscosity of the fluid. Okay. All right, so what this Reynolds number shows you is turbulence sets in around 2500 when the Reynolds number is 2500. Okay. So depending on the tube geometry, the onset of turbulent flow occurs when Reynolds number is greater than about 2500. Yeah. So Reynolds number depends on diameter, velocity, and viscosity. Yeah. Till what time does this class go? 10:50. Mm-hmm. Yeah. All right, so here's a tube whose diameter is changing. Okay. This is the flow rate. Flow rate is the area of cross section times the speed at which the fluid is flowing. Okay. Okay, let's say there are 10 gallons a minute flowing into the tube. How many gallons a minute are flowing out? Assuming there's no leaks in the pipe, same amount. And that's what this equation is saying. Okay, so the flow rate in here is equal to the flow rate out there. So what happened? But if the area increases, then the fluid slows down. Okay. All right, why do we care about this? Okay, when blood comes out of your heart, it's moving at, let's say, about 2 feet a second. Something like that. Okay, we'll give you the exact number later. If the blood flows by your cells at that speed, will you be able to exchange anything, nutrients or anything like that? No way. So you got to slow down the blood. How do you slow down the blood? Well, okay, so let's see. Okay, you constrict the vessel, you make area smaller, the blood will flow faster. Yeah. So you got to dilate it, okay? So when you're going by the cells, you're going at about 1 millimeter a second, super slow. So what you really have to do is you got to dilate it tremendously. Well, how the heck are you going to do that? Here's how you do it. You break it down into tiny capillaries. And the area of all that adds up to a large area, and that's how you slow down blood. Okay? Did you guys understand that? Yeah. All right, so here's another important thing to remember. Mr. Bernoulli captured all of this. Okay. Now, so this is the blood speed related to the area. Okay. Now, if the air, now here's a, well, okay. What Mr. Bernoulli found was the following. Okay. So here's a fluid. Okay. This dial measures the velocity of the fluid, and this dial measures the pressure. Okay. So here is the fluid flowing in this pipe, and it's measuring the velocity and pressure. Now it hits a constricted area, so what the fluid has to do? If the area is smaller, the velocity has got to increase, the speed has got to increase. Okay, so it's moving faster, the fluid is moving faster. And when it's moving faster, the pressure decreased. So you want to remember that. Whenever a fluid flows faster, the pressure at that location decreases. Okay? Mr. Bernoulli realized that. Okay. Now what he found was, so here's a fluid at different locations. The width is changing and all that. What Mr. Bernoulli found that the pressure at any location plus the kinetic energy per unit volume. Okay, this is related to how fast the fluid is moving, plus the potential energy of the fluid. These three terms combined are the same everywhere. So these three terms combined are constant. Okay. So for instance, so again, let me illustrate the fact. What did we just say? That the faster fluid is moving, the lower the pressure at that point. Okay. So P1 1/2 rho V1 square plus rho GY1 equal to P2 plus 1/2 rho V2 square plus rho GY2. Okay, so looking at this guy, Y1 and Y2 are at the same level. Okay, so I'm going to cancel these guys. They're equal, and so they get eliminated. Okay, and at this location, the fluid was moving faster. Okay, it was moving faster. This term was bigger, and so the pressure had to drop. Okay, this got bigger. This had to become smaller because the sum of these two has to equal that. So what I want you to remember is, anytime a fluid flows faster, the pressure there drops. Okay? So that'll be important. So that's what's going on in entrainment. Okay. So if you want to insert a fluid in another flowing fluid, that's what entrainment is. You take advantage of that. So for instance, this is how your perfume bottles work. Okay. So when you spritz a perfume or any of those spraying bottles, this is how they work. Okay. What you do is, here's a tube. So I'll, I'll do a bigger version of that. So here's the perfume bottle. There's perfume. Don't laugh at my diagrams. Your grade will suffer. Okay. So whenever you want to use an atomizer, what you do is you blow air across. Okay, so you're blowing air across here. So when you blow air across, the pressure in the air dropped, right? What was this? This was atmospheric pressure. This pressure is higher than this pressure, and that pressure will push the perfume up the tube, and the perfume gets caught in this flow of air, and now you have a mixture of air and perfume. Okay, so what happened was this fluid got entrained in this fluid. Okay, how did you decrease the pressure here? Because you increase the velocity. Okay, so entrainment is a insertion of one fluid into the flow of another fluid. Okay, now you might have seen this if you've done chemistry labs. You've used a Bunsen burner. Here's natural gas flowing at a speed. So natural gas is flowing, and the pressure in the natural gas is lower, and air gets in. And now air and natural gas will burn together. Okay? So we use entrainment of one fluid into another by using that phenomenon. Okay? Here's nature using it as well. Okay, these buggers are pretty smart. So what they realize is that air flows at a higher elevation, air flows faster. Okay, the further up you are, because there's no friction on the ground. Okay, so higher up, air flows faster. Okay, so these guys, burrowing guys, the one entrance is higher than the other. Here the air is flowing at a lower speed, so the pressure here is higher and pressure here is lower. Okay, because the fluid is flowing faster. And so this high pressure will push air through here. So just because of different elevation, now you have free air conditioning. So you have a continuous flow of air like that. Okay? And you wouldn't have that if both the entrances were at the same level. Okay? Okay, I'm going to explain these two terms and show you one graph, and then we'll be done. Okay? Okay, I got to tell you two things. So cohesion is the attractive force between two similar molecules. Okay? So cohesion is force of attraction between similar molecules. Adhesion is the force of attraction between dissimilar molecules. So for instance, cohesion is the attraction between two water molecules, and adhesion would be the force of attraction between water and glass, or water and the table. Okay, so adhesion is the force of attraction between two dissimilar molecules. Okay, now let's talk about one more thing. So here's a glass of water. Okay, this is a water molecule. Here's another water molecule. Here's another water molecule. Okay, these guys attract. So this guy will attract him. 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 What is the net force on this guy? Go ahead. 0. Very good. All right. Now let's do the following. Let's look at a molecule on the surface. This guy will attract him. This guy will attract him. This guy will attract him. What's the force on a molecule on the surface? Go ahead, you're right.
It is the same? You're talking
It's not 0. A molecule on the surface is being pulled down. Imagine a spring that is stretched. So this end of the spring is being pulled down. It costs you money to put a molecule on the surface. It costs you energy to put molecule on the surface. Do you want to spend a lot of money? No, you want to minimize your energy expenditure. So you don't want to put a molecule on the surface unless you have to. So for a given volume of water, the least surface area is that of a sphere. So if you have tiny droplets of water, what are their shape? A sphere. Okay? So when raindrops fall, that's why they're spherical. Okay, so the surface is under tension. Okay. All right, so that's why stuff like this is possible. Bugs can walk on water. The water surface behaves like a stretched rubber sheet, like a trampoline, okay, and it can support your weight. It'll support your weight as long as you don't break the surface. Okay, so here's what's happening on the surface of water. Let's say we put a small, tiny little object. Okay, there's tension in the surface, and that is what's supporting your weight. Okay, this tension, this component of the tension is canceling each other, and this component of the tension, these two are supporting your weight. Okay, have you guys ever seen a pin float on water? This is a metal pin again. So if you carefully place the pin without breaking the surface of water, you can make it float. Okay. All right. So surface tension is denoted by gamma. Okay, and here are the surface tensions, and this will become important next class. Okay. So I will stop now. Okay.